What's up my friends, welcome back! In the past video of this series we have seen the basics for the road to FPGA programming. We now know what are logic gates and how they work. In this video we will make another step forward and start learning about Verilog. So with no further introductions, let's get started! This project is brought to you by JLCPCB, which is a manufacturer of quick PCB prototypes for more than 10 years and is the site that I use for all of my PCBs. Once designed, upload your Gerbil files on the JLCPCB site. Get a full review of the PCB, select your desired settings and order the PCB for amazing prices. I've ordered 10 of my prototype PCBs for only $2 and received those in 6 days. Crazy, right? So order your quality PCB and make your projects look a lot more professional. What's up my friends, welcome back! This is my FPGA board and this is the FPGA chip. Inside of this chip there are many logic gates, but also already made blocks. We have flip-flops, ALU which is an arithmetic unit, multiplexers, memory, registers and so on. Always read the user manual of the chip that you use in order to know more. Before we even start, I would like to say you guys that my level of Verilog is not that high, since I've only used it for 1 year or so, but I would like to share with you what I've learned. Okay, so in this video I will introduce you to what is Verilog. First of all, Verilog is one variant of HDL. HDL has VHDL and Verilog. I will only focus on Verilog. To better understand, we have to first make a small compare between Verilog and a programming language, as for example C++. Verilog is not a programming language, but a hardware describing one. So for example, in C++ we already have the hardware inside of the microcontroller and we just tell it what to do. I make a software and that software will control the hardware of the controller. In case of Verilog, I create directly the hardware. I don't tell you what the module will do, but how the physical shape of the module will be, gates, connections and so on. For example, these few lines of Verilog will describe my module. We have the outputs, inputs and wires. We already know logic gates. In this case we have an OR, a NOT gate and an AND. So this doesn't tell me what the system will do, but how the parts of my module are connected. That's why I first showed you logic gates. In order to know what the module will do, you have to know what each part will do. I know I have 3 logic gates. The inputs are connected like this and between the gates I have 2 wires. The output is connected to a NAND gate. So as you can see, this describes the configuration of my hardware, where and how each component is placed. So if my FPGA has millions of gates, all I have to do is to define the connections, group them into modules, and finally achieve what I want. I'm not programming the hardware, I'm making it. So, why use FPGAs instead of microcontroller? Well, because with FPGAs I can do whatever I want. A good example I like to give is the use of PWM signals. Usually microcontrollers have a limited output of PWM signals because inside of the microcontroller there is a hardware for only that amount of PWM signals. But using an FPGA I can make each of the I/O pins to be a PWM signals if I want that, and usually an FPGA has a lot of pins. Also another thing, if you were to work with graphics or more complicated processing, FPGAs is a better solution. Not easier, but better. So let's start with Verilog. What better way to learn than a real example? First of all, to compile and upload my modules to my FPGA, I use Quartus. But to simulate I use Model Sim. Both softwares are from Altera and you could use the light version for free for students. So go to the link below, create a quick account and select direct download. Here you should download Quartus Prime, Model Sim and in my case the Cyclone 4 device, since my board uses that FPGA family. Select other device if you have a different FPGA. Now run the Quartus installation. Follow the steps and when asked for components, select to install both Model Sim and your device. in this case Cyclone 4. Click Next and install. Okay guys, we won't use Quartus in this video, but let's start with Verilog in Model Sim. Before we start, create a new folder, and this folder will be our work directory. I name my folder PWM Example. In this folder, create 4 more folders. One named MISC, Sim, TB and other circ. Now start Model Sim. Go to File and create a new project. Select the Sim folder as your project location and give the project a name. Now select a new file. Give the file a name and save it to the source folder. I name my module PWM Example since we will see a PWM signal simulation. Select Verilog and let's start. First create a module using the module and end module statements. Now give a name to the module. I will name it PWM Signal. And now open and close brackets. Here we define the outputs first and then the inputs of this module. In my case I have 2 inputs, which are the clock signal and the duty cycle value of the PWM signal, and 1 output, which will be the PWM signal. Next, you have to define those as inputs or outputs. So type input clock for the clock signal. But the duty value will be of 8 bits, so you have to do this. Type input and open brackets and type 7.0. So we have bits from 7 to 0, and then add the duty input name. This will create this input to be of 8 bits. Finally, output PWM for the signal output that will be of only 1 bit. Okay, so today we are going to work with the always statement. In this case I write always post edge clock. That means this loop will execute at each positive edge of the input clock signal. To create a PWM signal I need a counter. Each time the positive edge of the clock hits, I increase the counter by 1. But I don't have this variable counter, so I have to create it. This will be a register. For that, before the always I create a register of 8 bits once again and name it counter. The PWM output should be registered as well, but with a value of only 1 bit. Now with these 2 ifs, I put the PWM output to high or low each time that the counter value is higher than the duty cycle value. The first number of this means 1 bit, and the bit value is 0. So we write 1B0 for low and 1B1 for high. And our code is done. Now we have to test it, and this is very important. Create a new file and name it PWM test, and save it in the test bench folder named TB. In this file we first define the timescale of the simulation, in my case of nanoseconds. Next we have to create our test module. I name it PWM test and then I create 2 register inputs and 1 wire for the output with these names. Now I make the relation between the test file with my PWM module by using the UT unit with the same name as the module before and relate the inputs and outputs from my module with the ones in this test bench. Now I create a clock signal with a very simple always. The timescale is in nanoseconds, so after waiting 10 nanoseconds we invert the clock value and that would create a clock square wave with a width of 10 nanoseconds. Now we add the initial begin state. The clock initial state is 0, so let's give a duty cycle of our PWM signal of 124, which should be half width because we are using 8 bits. Add a delay of 100,000 nanoseconds and then change the duty cycle to 50, and then to 240, which should be almost maximum width since we have 8 bits. Now save and compile both files. If you get the green check mark, you are good to simulate, so let's start the simulation. For that, go to Simulate and Start Simulation, and here select the test bench file we have just created. Now from this list select your inputs and outputs that you want to see on the wave and add them to a new wave. Now select the simulation time. I select 100 milliseconds and hit run. And there you have it. Here we have the clock signal of 10 nanoseconds, so a frequency of 15 MHz. Then we have the duty value, which if I change it to decimal, I have 124, 50 and then 240. And finally, my PWM signal, and as we can see the width changes as given by the duty value, so the code works. Okay guys, now open Quartus and let's see one more extra thing. Create a new project and select the MISC folder as your project directory. Then select the PWM file we have just created and click Next. Here you have to select your FPGA, in my case is this Cyclone chip. Finish and now compile our project by pressing Ctrl K. Now go to Tools and select Rtl Viewer, and here we have our RTL diagram of our hardware. As seen before, we have the inputs and outputs. We have two registers, a sum block and a compare block. So this will be implemented in the FPGA. So we're not telling what this will do, but how the hardware will be connected. Well guys, that's it for today. We have seen a very simple example, but it's better to start with that. In the next video we will finally upload something to our FPGA and select our pins and a clock for a real simulation. Now that you know some basics, check more examples on the internet and stay tuned for future videos of this series. I hope that you enjoyed this video. If so, don't forget to click the like button like crazy and share this video with your friends. If you have any question about this video or any other, just leave it in the comment section below or my Q&A page. Also, don't forget to subscribe and watch all of my other great tutorials. And remember, if you consider helping my projects, check my Patreon page as well. And if you are new to this channel, click the subscribe button. Thanks again and see you later guys.